So I wanted to do another example of Webster's method of apportionment and Huntington Hill method of apportionment, where I just make up a problem. And this problem is based on the fact that when I was in the military, I knew someone who thought New England was either a country or a state, and they thought that Boston was the capital of New England. The sad thing is, I think they were from Massachusetts, but they thought New England was either a state or a country, I don't know, and that the capital was Boston. So today, in my example, New England is a country. So we have a country, New England, with 6 states. So I made this up. I haven't done the problem. I just made up the problem. I haven't done it yet. Sorry for going out of the screen like that. But I didn't want to do it because I wanted it to be in real time where I do it. I just made up some numbers. So we're going to use Webster's method. And then we'll probably do Huntington Hill. So obviously this country, New England, has 6 states: Maine, Massachusetts, New Hampshire, Vermont, Connecticut, and Rhode Island. And so that really, New England really does consist of those 6 states, but it's not a country. But in our example, it is a country. So I made up some. I don't know the population of these states. I could have looked it up, but I didn't want to. This is just an example. I tried to make it somewhat realistic, though. I said Maine was 1.2 million. Massachusetts was 6 million. New Hampshire, 1.1 million. Vermont, 800,000. I know Vermont's kind of small. I don't really know what the population is, though. Connecticut, 2.4 million. Rhode Island, 1.3 million. Those are probably pretty close. Massachusetts might be bigger than that, I don't know. So, if you look at the total population of this country of New England, I believe it's 12.8 million. I have to, yeah, that's about right. I added it up previously, so I hope it's right. So in my problem, I said that these 6 states have 130 seats that they want to apportion. So the first step is to find the standard divisor, and then you're going to figure out each state's standard quota. So the standard divisor is just found by taking 12.8 million and dividing by how many seats. So I need my calculator. I don't really, because I already did it. I already did this part. Some of the problem I haven't done, but you'll see. So it's the standard divisor, and I'm not going to even round. I'm going to just I'm going to write down what's on my calculator. That's the standard divisor. 98,461.53846. So, to find each state's standard quota, you just divide their population by that number. Now, and then for that, I'm going to round to 3 decimal places. Now, so I don't have to keep showing that on my calculator. I did also do that in advance, so I'll do that part in advance. Or I'll do that part without having to waste your time. by me looking at my calculator. So this would be 12.188, 60.93, 11.172, 8.125, Rhode Island, Connecticut, 24. Alright, so that's each state standard quota. So we're going to remember Webster's method uses conventional rounding. So what you get here is that you're going to round this up to 12, or down to 12 I should say. We're using conventional rounding. This goes up to 61, down to 11, down to 8, 24, 13. Now if you look, what happened when we did that, let me find an eraser. So that's how many seats each state gets. I'll just write seats. But if you add these all up, you get 56, 68. We have a problem. Boston, we have a problem. That number is too small. It's supposed to be 130. So what are we going to do? Well, in Webster's method, what you do is you change the standard divisor, which I erased, but I have written down. Let me write it down again. I'm notorious for erasing things before I should. Alright, so that was the standard divisor that we used. If I want that number to go up, I want all of these numbers to go up. I can make all these numbers go up by making this number smaller. So I want a smaller number than this. And I don't have to change it that much because I only want it to go up by 1. So I'm going to change this. I'm going to make it smaller. Making this smaller, when I divide each of these numbers by a smaller number, will make these bigger, which in turn, if I do it right, will make that bigger. If I do it right, perfectly right the first time, it will make it 130. So I want to make it smaller, but I don't want to make it too much smaller. I could just go down to 98 or 60. Let's go to 98,400. I'm going to make a bigger space because we might have to go back up, so I might have to write something here. There's no need to put a decimal. I'll just make it 98,400. That's what I'm going to make the new standard divisor. So all these are going to change. So let me erase this. So this was the standard quota using the standard divisor. So now I'm going to find the quota using 98,400. So I haven't done that in advance. I haven't done this part in advance where I checked. I wanted you to see that maybe it would take more than once. So I have to divide this by that. I have to divide all these by that. You'll probably be able to tell if it's a good idea. So this went up a little bit, but not enough, really. I don't think this is going to change it enough. What we need is one of these. This is already going to probably go, well, you know what? No, this won't go up far enough. What I think is going to happen, since this one only went up that much, this will go up probably past 61, but just a little bit, so it will still be 61. This will probably still be 12, that'll be 11, that'll still be 8. This one right here I should check next. I should check to see if this goes over 24.5. I bet it won't. Which means I need to even go more down. So 2.4 million divided by 98,400. Yeah, it did not go up enough. So this will probably give you, I imagine, I'm 100% sure actually, it will still give you 129. So I need to even go further down. And I don't even think, maybe going down to 98,400, or 98,000, exactly 98,000 would work. I think you want to check this one, because that's the number that might, when we use conventional rounding, this goes down to 24, but I think this might go up past 24.5. So that would be the one that the extra seat that we gain. So let me check. That's very close. This goes up to 24.489. So all these would probably still be rounded down, including that one, because that's going to go over 61, but it will be less than 61.5. So we know we need to go down a little bit more, but not much. Let's see, that changed it quite a bit going down 400. So I'm going to go down 200 to 97,800. So this is going to be my new divisor. My suitable divisor is what they say it is called. So the reason I'm making this video is because the last video I made that talked about Webster's method had a delay in it. But I'm not going to delete that. You can still watch that. So now you have two examples. In the other video, I didn't have to do all this work. So it's good to see it being done too. So let's see. Let's see what the new quotas become with the new divisor. Twelve point 270. So I'm rounding to 3 places here. 6 million 61 point. So yeah, I'm pretty sure now that this will work. Everything is going to stay the same basically, except for this one will go, I should have checked it before I did all this work, but this one should go over, I hope it does, or I just did a lot of work for nothing. Yep, it does. Good. So this works. So now we're still going to use conventional rounding. So the seats using this new divisor, suitable divisor, gives us 12, 61, 11, 8. Now this gets rounded up because we're using conventional rounding. Now if you add all these up, 57, you get 130. So using Webster's method, this is how the seats would be apportioned. You had 130 seats, and these were the population of the 6 states of the great country of New England. Alright, so since this video is running kind of long, I was going to put both do the Huntington Hill too, but I'll make another video for Huntington Hill.